So we've going to some exceptions to the octet rule, and I've actually already talked about a few of these, but let's just get these down on paper. The first exception to the octet rule is an odd number of valence electrons, and an example of this is nitrogen monoxide, NO, and we have nitrogen comes with 5, oxygen comes with 6, so I have 11 valence electrons to work with. So again, this situation, I connect them with a single bond. Now, on this process, I've spent 2, and I have now 11 minus 2 is 9. I have 9 left. Well, both of them want 6 more, so I need 12, but I only have 9, so I have a deficit of 3. Remember that? I said now deficit of 3, you don't jump up and follow the deficit of 4 rule, you fall back and follow the deficit of 2 rule, which means you make a single into a double. So I make a double. So now, but I just have to keep my budget because now I've spent 4. So 11 minus 4 is 7. Now I have $7 remaining. There's 7 electrons left to give out here. So both of them, my problem is both of them want 4 more, so I need 8, but I only have 7. There's nothing I can do to make up for that deficit. Now I just have to go back and say, well, who has a higher electronegativity? Who's further up and to the right? And that is oxygen. So oxygen becomes the king of the hill. And oxygen says, you know what, I'm going to get my 8. Nitrogen, you can have the remaining. So nitrogen gets the remaining. Now nitrogen has an odd number here, and this is our odd number of valence electrons. Now it's important in a little term here. What is that odd number? That odd number is called a free radical, and free radicals are very reactive, found in smog. Your body naturally produces free radicals, and you'll actually, if you look, watch on TV and you see commercials or talk about free radicals, like sports drinks commonly, or a lot of your juices, they'll talk about how they have antioxidants. Antioxidants help neutralize free radicals, which are very dangerous. Free radicals can cause cancer, they can cause illness in your body. It's very, very important. Again, you do produce a lot of free radicals naturally when you work out, so it's important that you have a good diet in your process and in your workout process there as well. You also drink plenty of water because you need to flush this stuff through. Incomplete octet is the third one, or second one, excuse me. Incomplete octet now means you have less than 8 around your central atom. And the ones it's going to show up with are 2 and 3, group 2 and 3. Boron's in group 3. And so boron, like you remember back to our chart, like 3 bonds and no lone pairs. So when you see boron here and you do a calibration, you say, okay, I have a boron and I have 3 fluorines. Boron gives you 3, fluorine gives me, I have 21, 24 total. I'm a boron central. I'll put my 3 fluorines around it, and then you say, oh, my boron needs a full octet, I have a deficit of 2. No, you don't. Boron only wants 3 bonds. You have no deficit. The problem is if you set a deficit of 2 and you start drawing out resonance structures saying, well, I have 3 single bonds, my double bond can be in either one of the 3, you're wrong. Boron is one of the exceptions to the rule. Again, anything group 13 wants 3 bonds. That's it. You do not show a full octet. Now group 2, beryllium, falls in, again, the same boat. To group 2, beryllium says, you know what, I have 2 valence electrons. All I want is to form 2 bonds. I do not want any lone pairs. And so beryllium, people will do in this situation, they'll say, oh, beryllium has 4, I need 4 more. Oh, I have a deficit of 4, I have to make 2 singles and 2 doubles, or singles and triple. Wrong. You messed it up. Again, beryllium's in group 2. It only wants 2 bonds. Now, remember I told you, and you actually learned this back in your atomic theory last unit, you realize that our transition metals by default have 2 valence electrons. So by default, all of your transition metals are going to be copycats of group 2. Like we see here, mercury has 2 valence electrons. It only wants to form 2 bonds. And so in this situation, it will look just like group 2. The third example here is expanded octet, and expanded octet happens in group 15 and group 16, and the reason why it happens is they come in contact with something with a high electronegativity. One of your guys in the upper right hand corner, your fluorine, chlorine oxygens, they're very, very bossy. They really, really want an electron. They have a high electronegativity. They're going to pull away from someone. And so what they're going to do, they're going to cause something in group 15 and 16 as you get a little larger. Will actually cause them to expand. Now this is going to happen in period 3. Go back to our atomic theory. Period 3 and below. You're not going to find this in group 15 and 16 in period 2. It has to be period 3 or below. 3 allow for the expanded octet, and we'll talk a little more about that as we move on, because that's where we get our D comes into play, all that good stuff. So anyway, so what happens now is our phosphorus has again, group 15 likes 3 bonds and 1 lone pair. But what if that lone pair gets separated? It comes in contact with fluorine, chlorine, or bromine, which says, you know what, I'm going to separate this couple. I'm going to now have 5 singles. Now 5 singles go out and form 5 bonds, and I have a full octet. And now you don't have to draw the actual Lewis structures around it. I mean, not the structure. You don't have to draw the valence electrons around all the chlorines if you don't want to. And this is kind of left as understood. But in this situation, we see that there are actually 10 valence electrons around my phosphorus, so it's expanded. Same thing happened in sulfur. Sulfur's group 16 has 2 pairs, and if those 2 pairs separate out into singles, now I have 6 singles. All 6 singles go out and form 4 bonds. I have 12 valence electrons around my sulfur, so an expanded octet. Coordinate covalent bond. A very, very important bond you understand here. And this coordinate covalent bond is a covalent bond, but the key is this. The lone pairs, remember normal covalent bond, each element involved in the compound donates 1. Well, in this situation, one of the elements donates both of them. We see this with ammonia, NH3, and ammonia has a lone pair here. And ammonia says, you know what? A hydrogen comes along, the poor little hydrogen was stripped of its electron, has a positive charge, has no electron to donate, wants to form a bond, and nitrogen in its Christmas spirit says, you know what, I will actually donate both of them, and I will actually, and being so kind, I will take you in. And so it actually donates both of those electrons to make up the bar, and that's what changed into ammonium, NH4+. Water can do the same thing. The formal charge of nitrogen in this situation was a +1. Water can do the same thing in this situation. So water will actually, again, H2O has 2 lone pairs. And so another hydrogen comes along, and water says, you know what, I will take you in. So it says, I'll flip the bill, and I'll pay for both the electrons to form a bond. And so hydrogen joins up with water and forms into hydronium. And now my oxygen in the central has 6 minus 3 bars minus 2 dots gives me also a +1 formal charge now for my oxygen.